So our third speaker of this first session is Brian Jarvis, in this joint work with Chris Guy in accelerating class with McEliece with PUF-based key storage. Thank you, Brian.
Yeah, thanks for having me today. All right, so yeah, thanks for the introduction. My name is Brian Jarvis, and yeah, I'll just move forward since you already read this slide. Yeah, just a little bit about me first. So I'm a student at George Mason University. My advisor is Dr. Chris Guy. We work in the cryptographic engineering research group there. I defended my thesis in 2015, which was on the topic of error correcting codes for physical unclonable functions. I'm also just a part-time student, so my day job is as a software engineer at Amazon Web Services cryptography. So about this talk today, this is a research work in progress. It's going to be the basis for my forthcoming PhD proposal. And the idea was to combine two of my areas of interest, which are physical unclonable functions, as well as optimization for code-based crypto systems. So that's the overlap of those two areas. So the motivation behind this is that I'd like to have a secure key storage, which is what you would typically use a physical unclonable function for, and then also be able to optimize with a hardware-software co-design the classic McEliece crypto system, and then find which hardware is common between those two so that there's a hardware savings that gets realized so that you're not implementing the same hardware two times in order to achieve both of these goals. So first I'll start with a little bit of background about physical unclonable functions. So these are cryptographic hardware primitives. And the idea is, as you could kind of see in this illustration, if you have three, or it could be any number of chips, that you put an identical circuit on each one of those chips. And then due to the unavoidable manufacturing variations that occur at the circuit level, they produce different responses. So you'll get three unique responses for three unique chips. Extend that out to n unique chips, and you can kind of think of this as like a fingerprint, but for your circuits. So you could use this for hardware authentication of individual devices. You can also use this for secret key generation, where each device generates its own unique key. So there is a slight problem when you use PUFs alone. So they are susceptible to fluctuations, like in terms of voltage or temperature. So on regenerations, you might get a slightly varied value. So maybe you've generated it one time, you plan to use that key that gets generated from that PUF, but then you have variations in some of these environmental factors, and then all of a sudden your key is different because the PUF itself was susceptible to fluctuations in those areas. So there is a solution to this, which is to combine your PUF with a fuzzy extractor, and the fuzzy extractor inside of it has an error correcting code. So you can kind of think of the fuzzy extractor as a way to accommodate those fluctuations that would produce errors. So when you run your PUF input through the fuzzy extractor, you produce the key, just like in the original slide. However, you also produce a public helper data, so that when you go to regenerate that PUF in the circumstances which might yield PUF error bit errors, you now are able to correct those bit errors along with the helper by using the public helper data and regenerate that same key again. So you get reproducibility. You also get uniformity because you have a cryptographic hash function inside of the fuzzy extractor. So any input into that then gets more evenly distributed, uniformly distributed. And now the output of this fuzzy extractor can be used as a cryptographic key. So the hypothesis that was based on a few observations is that since classic McEliece is using the GAPA code for encryption and decryption, you can also use the GAPA code inside of a fuzzy extractor, because the definition of the fuzzy extractor uses a linear block code for error correction. And so as long as you meet certain entropy considerations and probability of failure considerations, you could use the GAPA code. And so we can combine these two so that you have the fuzzy extractor for secure key storage. Oops, I'm sorry. I lost my screen for a second. There we go. So you have the fuzzy, so you have the fuzzy extractor for secure key storage, and then you're also able to reuse the components of that fuzzy extractor for the classic McEliece encryption and decryption. And those common components are the GAPA encoder and decoder. So going a little bit deeper into the fuzzy extractor circuitry, this is the definition from Dotis and their co-authors in 2008. And the generation of the secret key occurs by taking the PUF output and putting it through the entropy extraction block, which is it could be a cryptographic hash function. And then at the same time, a public helper data is generated by producing a true random number and then encoding that with error correcting parity bits. And then those two get XORed to produce the public helper data. On reproduction, the public helper data gets XORed with the PUF reproduced value, which now could contain some errors, so that now the error correction code decoder is able to correct those errors to recover what was originally generated by that true random number generator in the top block. Then when you re-encode that and then XOR it with the public helper data again, you've now recovered the original PUF value, so that when you run it through that hash function again in this diagram. Now, I did mention that there are entropy considerations you have to take into account. So PUFs are typically expressed in terms of entropy density. So if you have an n-bit PUF, you don't get n full bits of entropy. You typically get some percentage of that. So let's say 85%. So just some easy numbers. If you had a 100-bit PUF, you get 85 bits of entropy out of that. You also have to take into account the entropy loss that comes from the error correction code, because the n minus k parity bits can't be used towards the level of entropy. So you would, to calculate the remaining entropy h on this system, you would take the entropy density of the PUF, minus the n minus k bits. So combining this together with my design is using the GAPA encoder and decoder. I've selected the NIST security level 5 submission for the classic McEliece and the largest parameter set of those. So it's 8,192 bits of the code word size and 6,528 bits as the message size. Putting it into this system, you want to preserve at least 256 bits of entropy on the value k, because the idea is that I would like to use that to seed the key generation of classic McEliece. So using that equation that I talked about in the previous slide, you would solve for the size of the PUF that you would need. So you would end up with 2,259-bit PUF. Now, if I just pop back to the previous slide for a second, you'll see, there they use the same size of PUF as the output of the encoder. You could do that, and you could use an 8,192-bit PUF. However, you would actually end up with much more entropy on that value of k than you actually need. And also, you're now utilizing a lot more hardware resources than you need, because the PUF can sometimes be quite large, depending on what type of design of PUF you use. So here I've arrived at just exactly the size of PUF that would be needed to generate 256 bits of output. And then to accommodate the size difference, it's padding zeros at the end of the PUF before it gets XORed with the encoded random number. And then that just has to be removed off when you run it through the regeneration circuit. And the two circuits are illustrated separately here, just for it's easier to reason about them that way. But these actually would be reused hardware components, so they're color coded. So the hash function would be the same hardware element. The GAPA encoder would be the same unit, and the PUF is the same. So this allows for reaching the highest level of the classic McEliece encoder and decoder, and then that way you can reuse the encoder and decoder that is used in the fuzzy extractor. So that way you're able to offload from, if you have your classic McEliece software, you can offload that into the fuzzy extractor's hardware. And then you preserve 256 bits of entropy on the secret value k, so that it can then seed key generation. So there's some previous work in this area. In 2021, Kostelobros and their co-authors, they performed a hardware-software co-design using Vivado HLS, and they profiled the software to identify which were the most expensive areas. And so they identified the matrix systematization step of key generation and error correcting code encoding of encapsulation and field element matrix generation and matrix extension and syndrome computation of decapsulation as the most expensive areas that they wished to offload into an FPGA. And with their implementation, they saw speedups using a Xilinx Zinc UltraScale Plus CPU FPGA system on a chip combination of 55.2x on key generation, 3.3x on encapsulation, and 8.3x on decapsulation. So we observe here that this is almost all that's needed for a fuzzy extractor, because for the encoder and decoder, you would just need to add the Berlekamp-Massey decoding to complete the decoder. And then the error correcting code encoding completes the encoding side. So you can then go beyond this, because in the fuzzy extractor, you would, to have the complete fuzzy extractor, you would need to have the complete GAPA decoder. So you will have some additional gains by having the Berlekamp-Massey also implemented in the FPGA. Additionally, since the fuzzy extractor does need that SHA-3 function, you would be able to reuse that for the couple of operations that occur during classic McEliece encapsulation and decapsulation. So going off of the numbers from that Kostelobros paper, where they achieved a certain amount of speed up by moving their selected components into hardware, we could go beyond that and have up to an additional 33% of encapsulation time saved and additional 27.6% of decapsulation time compared to the reference code. So another prior work from Wong and the co-authors in 2018 implemented classic McEliece in a Intel Stratix 5 FPGA, and they implemented all components, so key generation, encryption, and decryption. So you can see in the block diagram of the decryption module, they have a Berlekamp-Massey module implemented. And so this kind of fills in the missing piece from that Kostelobros paper that I mentioned before. And so the expected results that we should see are that we can go beyond the 8.3x speed up of decryption because of bringing in that Berlekamp-Massey implementation. Additionally, having an actual HDL implementation is going to be more performant than an HLS implementation, which was what they had used in the Kostelobros paper. So comparing the two implementations here, on the Kostelobros paper, they had using a Cortex A53 at 1.1 gigahertz and the Zinc at 333 megahertz, and just the operation being just syndrome decoding, not a complete decryption. They were running that at 2.22 milliseconds. The Wong implementation used the Stratix 5 FPGA at 289 megahertz, implemented the entire decryption operation in just 0.12 milliseconds. So that just kind of illustrates the difference of the HDL versus HLS, but then also bringing in the Berlekamp-Massey into the FPGA. So now we also expect to be able to accelerate the encapsulation and decapsulation key derivation operations by reusing that fuzzy extractor SHA-3 component as well. And then all of this allows us to generate the secure key, perform secure key generation using the output of the fuzzy extractor as the seed. So just as kind of another big picture diagram of what I've been describing is, so the fuzzy extractor has these components, the error correction code encoder, the error correction code decoder, and the SHA-3 hash function. So the output of the whole entire fuzzy extractor would seed key generation. And then within the encapsulation operation, you have encryption and key derivation. The encryption would be able to leverage the encoder of the error correcting code from the fuzzy extractor. On decapsulation, the decryption would be able to leverage the decoder of the encapsulation of the error correcting code, and the key derivation of each operation would be able to use that hash function. So like I said, this is a work in progress, so there's still a lot to do. PUF design is one area. For example, we could implement that in hardware. There are also some CPUs which have PUFs inside of them, but we would still need to evaluate them for probability of error, because depending on how many bits are susceptible to flip in a PUF, that bit error rate drives how many errors the error correcting code needs to be able to correct. And so if you exceed that, then you now have a failure on the fuzzy extractor. So need to have sufficiently low probability of failure. Additionally, there are different fuzzy extractor constructions. For example, there's the one that I showed several slides ago, which is the DOTIS definition, but there are others which use multiple random number generator inputs, and that allows, for example, the ability to change the secret should one become compromised. So there's some advantages there that are worth exploring. And then additionally, actually implementing the software hardware co-design across multiple hardware vendors. You know, I'd like to get a diversity of manufacturers such as a Xilinx Zynq and an Intel Agilex, for example. There will, of course, be some software that remains that is not offloaded to hardware. So further optimization using either vector instructions or assembly or some combination of the two. And then I'd eventually like to build this into a real world application, such as implementing a secure key exchange protocol. Some references, and I thank you for your time today. I welcome any questions.
Thank you, Brian. I will try to either you speak very loudly or I will try to repeat them for Brian.
Yeah, I was going to say the room. I can't hear the room super well, so if someone could repeat.
You can hear the room. Okay, let's try. Oh.
Which kind of puffs did you use in your design? So which SRAM puffs or?
Did you hear the question, Brian?
I heard the word SRAM puff, so I assume it was a question about puffs, but
so Thomas was asking what kind of puffs did you use?
So this is not yet implemented yet. So it's still in the planning phases, and this is sort of the research in progress. But the idea would be to decide whether to use, like, which type of puff to use. It could either be, I mean, our ring oscillator puffs are often used in literature, SRAM puffs, as you mentioned, but there are also some puffs that are built into certain CPU FPGA system on chips. So it would be a matter of evaluating if any of those built-in components have sufficiently low bit error rates such that the probability of failure of the overall fuzzy extractor system is low enough. If not, then one could be implemented in the FPGA as well, and that would be almost an entire research exercise unto itself, is to identifying the right puff to use. So.
Thank you.
Okay. We have more questions from Brian. Okay, so it looks like there is no more questions. We are a little bit early, but please, first let's thank Brian again for the talk.
Thank you.